Sail-equipped motor ships, which use wind energy to supplement engine power, are attracting increasing attention globally as world fuel supplies dwindle. Recently, a two-year effort in Japan led to the creation of the world's first modern sail-equipped motor cargo ship, the Shin Eitoku Maru. Until the end of the 19th century, large sailing ships played a leading role in global ocean transport. Nevertheless, such ships had inherent drawbacks, including the need for large crews to handle the sails and favorable winds to maintain their schedules. In the 1980s and beyond, sail-equipped motor ships, their fuel-powered engines, aided by free wind power, promised to reduce fuel consumption. Such ships would need no additional sail-handling crewmen, besides having the stability, maneuverability, and cargo capacity of current vessels. Selection of the optimum system of sails was critical. Starting with several experimental sails of different types, wind tunnel tests determined the optimum arrangement of sails. Rigid sails resembling airplane wings. Soft sails made of canvas. And triangular sails. The wind tunnel test called for gradually altering a sail's camber, their upward curve or arch, and angles to the wind. After 50 different tests for each, their aerodynamic characteristics were computer analyzed. The wind tunnel test data was verified by sea trials on the 25-meter ship Dale. The rigid sail nearest the bow was a laminar or smooth flow type, 7 meters high, 4 meters wide, and foldable in 3 sections. The soft midship sail was similar in size. The aft sail was triangular. A remote control sail handling system spread, folded, or turned sails individually or together. 3 months of sea trials confirmed the wind tunnel tests. The rigid sail was best overall. It produced considerable propulsion from winds from any direction more than 20 degrees from right or left of the bow or front of the ship. The tests also showed the automated sail handling system's practicality, safety, and fuel economies. Design of the commercial use sail-equipped motor ship, a small tanker, followed. The 699 gross ton tanker would be 66 meters long, 10.6 meters wide, 5.2 meters deep, with a 4.4 meter draft. A hull longer and narrower than conventional designs reduces wave resistance. A 1,600 horsepower diesel engine powers the ship. along with 2 sets of rigid sails designed to optimize fuel saving, maneuverability, stability, cargo handling, and other capabilities. Each sail can revolve or fold in 3 sections. Sail designs were based on the research data, plus wind tunnel tests of ship models, laminar flow rigid sail designs. The 2 sets of rigid sails are 8 meters wide and about 12 meters high. Their combined surface area, about 200 square meters, reduces to about 40 square meters when folded. Tank tests were next. The hull form design maximizes fuel-saving capabilities. Large rudder and bilge keel improve roll damping characteristics. Response to waves and winds of various velocities and directions was confirmed by tank test simulations of weather and sea conditions. At normal film speed, movements of wind and ship were erratic. But slow motion, filmed at 5 times normal speed, revealed clues to ship behavior at sea. Storm conditions are also simulated. Testing with varying wave and wind conditions confirmed the ship's seaworthiness. To further ensure the best design, other capabilities, including stability and turning, were also carefully verified. The basic goal of the sail-equipped motor ship is minimizing fuel consumption. To do this, the ship employs microcomputers to maximize the wind's contribution and adjust engine output accordingly. Speed and direction measurements are used by microcomputers to determine how the hydraulic drive should trim and angle the sails to make best use of existing winds. The same computers, meanwhile, reduce engine output by the wind thrust gained, maintaining the ship's speed. Except when the wind is less than 20 degrees from straight ahead, the sails gather at least some wind energy. By contrast, if wind speeds exceed 20 meters per second, the sails fold automatically and turn to minimize wind pressure on them. No matter how great the wind, engines always operate to maintain steering control and moderate wind effects. After 2 years, construction of the ship commenced. With the mast's stationary section welded, the ship began to take shape. Wind direction and speed meters, sail handling machinery, vertical push rod and hydraulic cylinder, sail rotation turntable, and miscellaneous control machinery and equipment. Launching day. The building berth is surrounded by those who designed and built the unique vessel, created by Nippon Kokan, the Shin Eitoku model. later, final outfitting was completed and official trials were passed. A crucial question remained. At each given speed, how much wind energy will be gained, allowing engine output to be reduced? Extensive tests and experiments matching wind speed changes and changing course to fit wind direction charted this critical energy-saving effect. Precise energy gains were also measured. For example, a 10-meter wind at 110 degrees from straight ahead permits a 20% fuel saving over motors alone. Sail trials proved the ship's maneuverability. Turning radius and crash astern measurements were very close to conventional ships. Tests of the microcomputer systems verified its components. Sensors, activators, monitors are normal, the key to maintaining the designated speed. Sail tests and handling training took only 2 days. The 4-story polyester sails can be handled easily, both manually and under automatic control. This allows the ship to be operated by 10 men, no more crewmen than conventional vessels. Sails can be stretched or folded in about 2 minutes. Currently, Shin Eitoku Maru, a product tanker, is sailing the coastal waters of Japan and the East China Sea. On the average, sails are used over 60% of the time, achieving great fuel savings even under tailwind and following waves. The ship also shows excellent seaworthiness and course stability. Today, Shin Eitoku Maru functions as a safe, economical, ocean-going merchantman. Adding auxiliary sails to 20 to 30,000 ton vessels will further improve their effectiveness. And retrofitting of conventional ships with sails is also practical. The sail-equipped merchantman, utilizing an ancient mode of travel, the wind, combined with today's high technology, is designed to meet the requirements of the changing global energy situation.